All right, here we are for Honors Physics Electrostatics Worksheet 3 on Coulomb's Law calculations. We're taking a look at question 8. Question 8 says two pith balls shown in the diagram have a mass of 1 gram each, and they have equal charges. One pith ball is suspended by an insulating thread. The other charge is brought to within 3 centimeters of the suspended ball. The suspended pith ball is deflected from its rest position, so it is getting repelled over, until it forms an angle of 30 degrees with the vertical. At this angle, the ball is now in equilibrium. Okay, so this guy is being repelled over like that angle. All right, draw the force diagram depicting the forces acting on the suspended ball, the ball on the end of the string here. Okay, so let's go ahead and sketch that out. Okay, I'm actually going to go ahead and draw that diagram bigger on my page. I always like to have the diagram right there on the page where I'm doing my work, so I'm not having to flip back and forth from page to page. So take a look at this. You're like, okay, I've got a pith ball over here and another one over here that's on the, it's on the end of a string. Okay, it's been deflected from vertical to an angle 30 degrees. Okay, and we know that the separation distance is 0.03 meters. That's 3 centimeters. Okay, is how far over it's been deflected. There we go. Okay, we also know the two charges are the same. Okay, and the mass of each is a gram. Okay, now let me tell you the mass is a gram. I pretty much just immediately say, wait a minute, I know that for mass I always want to use kilograms. So I'll just convert that right away. It's 1,000 grams in the kilogram. So if I only have 1 gram, that's 1/1000th of a kilogram, 0.001 kilograms. Okay, right away, do that conversion. Okay, so it's in equilibrium at this point. So like, okay, let's do a force diagram for this guy. And I'm actually just, skipping ahead. It says they want you to find the gravitational force on the ball, electrical force on the ball, and then we'll find the charge on the two balls. So thinking about this pith ball, if we did our force diagram, notice I'm doing a free body diagram off to the side. You'd say, okay, ranged forces, there would be gravity, okay, which I'm going to label as mg. And then there's an electrical force. Now, we know this thing wouldn't be hanging at this weird angle if it wasn't being shoved to the right. It's being repelled to the right electrically by that other charge, the same height. That's it for ranged forces. Okay, gravitational. Now we got to worry about electrical forces also. It's another kind of ranged force we can have on our force diagram. Okay, now let's talk about contact forces. So what's touching the ball? You say just that string. Is the string being stressed? Yes, it is. There's a tension. Okay, it's going to go that way. Okay, it will be that tension force. All right, and that's it. That's the only thing touching is the rope, and it's being stressed, so there's a tension. That's it. That's all the forces acting on the pith ball. So now what they'd like us to do is calculate the gravitational force. So part A of the problem was doing the force diagram. Part B, they want us to find the gravitational force. You know what I'm saying? Mg is how big? And so you say, well, to do this, you say, I'm going to need to know some other forces. I know it's in equilibrium, and that means my forces have to balance out, right? So you say, well, let's pick some coordinate axes. And you say, well, we're not really moving anywhere. It certainly would be convenient with a horizontal force and a vertical force here to just use x, y as my axes, horizontal and vertical. X, y, let's call up and right positive. Then I would need to split any forces that aren't going along these axes into components that go along the axes. I'll have to split that tension force up. Let's go ahead and do that. That's my horizontal vertical components. We were told that the string is at 30 degrees from vertical. And so here that tension's along the string. So that's also 30 degrees from the vertical, which makes this side the adjacent. This would be t times the cosine of 30. And this side is opposite that angle. It's not touching the angle. So this leg is the opposite leg, t times the sine of 30 degrees. All right. I'm trying to find mg. That's a force in the vertical axis. Let's do a sum of the forces in the vertical axis. So that's where I'm going to go next. I'm going to say, let's take a look at the sum of the forces in the y-axis is mass times acceleration in the y-axis. But we know we're in equilibrium, so that acceleration is 0. My forces balance out. They add to 0. When my forces, we're going up minus down, so it'll be t cosine 30 minus mg. Equal to ma. But my acceleration is 0, so it just balances out to 0. You say, okay, I'm trying to solve for the gravitational force. Oh, wait, why did I do it this way? I can solve for gravitational force right away. It's just m times g, and I was given the m. Oh my gosh, that's okay. You know what? I'm not going to erase this or scribble through it because you know what? I bet I'm going to use this in a later part of the problem. So let's just hang on to that. Just mg is just mass times 9.8. Oh my gosh, I'm so sorry. The mass is 0.001 kilograms. And g, of course, is 9.8 near the surface of the Earth. So that's just going to be 0.0098 newtons. Sorry, that's the gravitational force. Let's see here. Then they want us to find the electrical force acting. Okay, this is where we're going to need this information. Okay, so here, this is part of our solution for part C now. See how that snuck right in there. Okay, hey, we want to find the electrical force. That's a force in the x-axis. Let's do some of the forces in the x-axis. Applying Newton's second law, sigma F is ma, this time to the horizontal axis. We're doing forces right is positive, so right minus left. So you say, hey, that'll be Fe to the right. So I make that positive minus t sine 30 going to the left. Okay, that's got to equal mass times acceleration in the x, except we know that we're not accelerating anywhere. We're at equilibrium, so that's got to add to 0. Okay, so here we go. I'm trying to find Fe. You say, look at this. The only other variable in this equation is T, the tension. If I knew the tension in the rope, I could find Fe. You say, well, look, tension in the rope, that shows up over here. You say, well, look, this equation has tension of the force and tension force in the rope and gravitation. Well, the gravitation we just solved for. So actually, we could use this one to find T, and we could plug the T value in there and get Fe. Or we could go ahead and do all the substitutions right now and just sub in our numbers once in the calculator. I'm going to do that way. So I would rearrange this equation, and I would get that T is going to be equal to mg divided by cosine 30. And we could go ahead and substitute that in there where we see T, right? That would make sense. If I do that, can I go ahead and do another algebra step? I'm going to go ahead and move this t sine 30 to the other side and then substitute in. So that Fe that I'm trying to solve for will be equal to T, and that's this mg over cosine 30, times the sine of 30. So you say, well, at this point, we know the mass, 0.001 kilograms. We know G, 9.8. We can solve for that Fe. So the Fe is going to be equal to, that mg ended up being 0.0098, right? Sine over cosine, that's just tangent of 30. Okay, so I can punch that in my calculator. My calculator tells me that electrical force should be 0.00, we'll round 566 newtons. Teeny tiny electrical force. That's okay. We have a teeny tiny gravitational force too, right? It's a really tiny lightweight pith ball. All right. And so now we want to do in part D is they say, hey, can you calculate what the charge is on the pith balls? That's this little Q guy. Now, both these guys, Q1, Q2, but they told us in the setup that the two charges are the same. And so I could really just have one variable Q because they're both the same. They're both Q. Hey, how am I going to find that charge? You say, I just found the electric force, right? You say, oh, well, in the equation for electric force, in Coulomb's law, there is a place for charge. So let's start with that. So for part D here, we're going with Coulomb's law. Electrical force is that Coulomb's law constant times the charge of the first object, charge of the second object over that separation distance squared. We know K, Coulomb's law constant, 9 times 10 to the 9. The two charges are what we're trying to find. We don't know what they are. We do know that they're both the same size, though, right? They tell us they're the same size. So Q1 equals Q2. So I'm just going to do this like this. Actually, electrical force we just solved for, right? I'm just going to go ahead and sub the values in now. I normally would go ahead another step and then rearrange, but I'm going to be honest, I'm getting tired. Let me just crank this out. The two charges are the same, so it's like Q times Q, Q squared. And that separation distance we know is 0.03 meters, 3 centimeters. So I can solve this for Q. Gosh, this would have been nicer if I had. Okay. What did I do here? I got to divide, multiply by something, divide by what's on top, right? 9 times 10 to the 9. There we go. And then I have to take a square root, right? There we go. So that's what we end up with. Okay, punching that in the calculator. Okay, I have that answer, the previous answer in my calculator still, so I'm just going to leave that, times 0.03 squared divided by 29 times 10 to the 9. Okay. And then I have to take a square root of that. And I get that charge is 2.3, we'll round it to 8, times 10. My calculator tells me E negative 8, so it's times 10 to the negative 8. Okay, and so that's what the charge has to be on the two pith balls. Okay, well, let's go ahead and double check my solution against Mr. Wishway's answers in the back of the packet. 2.38 times 10 to the negative 8. Hey, I feel pretty good about that. All right, so that's that problem. So the key points here, if I was going to point some things out about this problem. Okay, gosh, I hope that was on camera at the end there. You say, hey, we do force diagram like you normally would, treating Fe as another ranged force. Okay, the electrical force. We do coordinate axes as usual. This thing was in equilibrium, in fact, it was at rest, so it's not like it had any motion to worry about. You could technically do your axes whatever's convenient. Certainly, so that two of those are along the coordinate axes would be the most convenient way. So then we went ahead and did coordinate axes, split things up into components, and looked at our sum of the forces in each axis, in the y-axis and in the x-axis, and did a little subbing around. No big deal. Okay, and so that's solving a force problem with electrical force in it.